Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Manuel Hohmann. He got his PhD, or the German equivalent, Doctorate Nat, from the University of Hamburg in 2010, and he got his habilitation at the University of Oldenburg in 2022. And since 2021, he is an associate professor at the University of Tartu. Thank you, Manuel, for agreeing to give the talk. The stage is yours.
Okay, thank you very much for the invitation. So I would like to present some work today together with Paul Hohmann, who is my PhD student at the University of Oldenburg, and who has done most of the heavy calculations that are behind this work, most of which I will actually not show here because they are quite lengthy and intense. So I will try to rather focus on the basic results and the overall framework that we're working with here. So let me start with a very brief motivation. So we are interested in open questions about gravity theory, and some of the most important unsolved questions are: how can we quantize gravity? Can we find a unified theory of gravity and the other interactions from particle physics? And related to this, can we understand gravity as a gauge theory? And if so, what would be the group that we have in this gauge theory? And here in particular, I would like to discuss a few formulations of gravity, in particular general relativity, which have the structure of a gauge theory in some sense of either the Lorentz or the de Sitter group. And in particular, I would like to focus on the actions, the following actions: the Stelle-West action, MacDowell-Mansouri action, the Palatini and the Plebanski action, which have slightly different structure and which I would like to understand within this framework. Now, if one looks at these, then there are some open questions. So some of these, or in the Stelle-West action, for example, has a de Sitter or anti-de Sitter symmetry. You can write it either way. And the question is then how we get the usual Lorentz symmetry. I will show you how this is done in the Stelle-West case. And yeah, I will explain some alternatives as well. And the question is, can we describe all of these theories within some unified geometric framework, because they have a bit different geometric interpretation. And here in particular, I would like to have the following geometric approach. So I would like to base these theories on Cartan geometry, where we have an interesting structure. It has, by construction, there is a tetrad in the Cartan geometry, and also some way to perform symmetry breaking, which I would like to explain. Then here, slightly technical detail, I will be working with spin groups and spin algebras, which are, the spin groups are basically just a double cover of the corresponding orthogonal groups. It's just a technical detail because we would like to couple spinors at some point. I will not go into the details here. And if one looks at spinors, then also it's a small step going from the spin algebras to the Clifford algebra. And I would like to explain how working with Clifford algebra actually turns out to be a very nice framework for giving these theories a unified description. So let me give a brief outline of the talk. I will first start with some mathematical preliminaries, discussing mostly the Clifford algebras and Cartan geometry, and also introducing the notation that I will be using here. Then I will give a very brief review of the formulations of general relativity I'm discussing here, and then show how these can be written in terms of this Clifford algebra construction. So let me start with the mathematical part here. So I will discuss only real Clifford algebras. So what are the ingredients we need to define a real Clifford algebra? We need a real vector space of dimension n, and this dimension n I will split into p and q, because I would like to equip this with a symmetric bilinear form, which I call eta, and this should have the signature p, q, where by this I mean P times plus and Q times minus signature. Now, how we construct the Clifford algebra is the following. We start with the free associative tensor algebra generated by this vector space V. So basically all the vector spaces over all formal products of these elements of this vector space. Then we define a two-sided ideal within this tensor algebra, which is generated by these elements that are written down here. And then the Clifford algebra is simply the quotient of this tensor algebra by this ideal here. And if one follows this construction, one finds it's a real associative algebra of finite dimension, the dimension here being 2 to the power p plus q. You might think of gamma matrices here if you're a bit less inclined towards the abstract mathematics. So the gamma matrices appear as a representation of certain types of Clifford algebra, usually Lorentz algebra, or its complexification to be more precise. But here I don't assume any particular representation. So I'm really just assuming the abstract algebra elements here. So if you are more prefer to work without any particular representation, this is what this is mostly about. Here I will in particular focus on the case that this P and Q are either 4, 1 or 2, 3. And well, you might be a bit wondering why am I kind of flipping the signature, which one gets the plus and which one gets the minus, which one is space and which one is time. This is just for convenient because later I would like to do a symmetry reduction and I want to write it down in the unique or unified way when I basically split down along a positive direction. So the Clifford algebra is naturally decomposed into subspaces, where each subspace as a vector space is isomorphic to the exterior power of this vector space V. And in particular, if you look at the highest power here, which is k equal to p plus q, there is a volume element. This is a one-dimensional space, so there exists a unique element up to a sign such that this squares to 1 up to a sign again, which in this case that I'm studying here, this sign amounts to -1 for these particular values for p and q that I'm interested in here. We can also define a trace on a Clifford algebra, where it is simply defined here that on the unit element it equals to 1, and on all these other vector spaces it is equal to 0. And why do I call this a trace? I call it a trace because it's well, defined here as being linear on these vector spaces, and in particular because I would like it to be have a cyclic symmetry or invariant under cyclic permutation of this Clifford algebra product under the trace. So again, you might think of a particular matrix representation, then it would indeed be related to the trace, but one has to be a bit careful. For example, in a complex case, one has to make sure that this would be only the real part, for example. So this is not exactly the same thing as the matrix trace. If you represent a real Clifford algebra in terms of complex matrices, for example, you have to make sure that you only take the real part here. Yeah, if we write this in a basis, we pick an orthonormal basis of the vector space V, then we can of course expand this by linear form in this basis, and we have this relation here for the product of the basis elements in this Clifford algebra, and we can define these subspaces by the ordered product of this distinct elements of this basis here. And we can pick one of the two sign choices for this volume element, basically providing an orientation by writing it this way. This is, of course, changes if you change the orientation of this basis. Now, in the following, I will be working with some kind of symmetry reduction, and this is now introduced as follows. I first of all pick an element of this vector space, an arbitrary element V, but with the restriction that it is normalized, and normalized such that it is actually positive norm in this particular case. In other words, if I recall the formula for the Clifford product, it should square to the unit element 1. Now, this induces a decomposition of this vector space V into orthogonal subspaces. There is the subspace which is parallel to this Y, so it's just a span of this one element. And because I have a non-degenerate bilinear form on this, I can also define the orthogonal complement, which is then again equipped with a bilinear form with a signature where I have reduced this P by 1. So here, this is where the choice of the signature goes in. I want this to be, for simplicity, I want this to be equal to 1. And then I reduce the P. Of course, I could also just swap P and Q if I wanted to. Now, the Clifford algebra of this one reduced dimension, P minus 1 here, is now actually generated by this orthogonal complement, because this is, of course, again, a vector space with a bilinear form now of signature P minus 1 Q. And it turns out I can write my larger Clifford algebra in this form as a direct sum of my smaller Clifford algebra and this product here, where I simply multiply each element with this vector Y here. And also the volume elements are related. I can again pick a particular sign of this. If I have picked the sign of this omega here on the larger algebra, then I multiply this with Y, and I call this my volume element now of the smaller algebra. And of course, it again satisfies this nice formula here. So this is essentially the same formula, just one dimension lower. Now, this element Y will play a central role in the construction here. And in particular, what we can do with this Y is we can multiply any element of the Clifford algebra either from the left or from the right. And this defines an action of this element Y by either left or right multiplication. And since it squares to 1, it means that the action of Y that is defined like this must have eigenvalues plus or minus 1. So we can define projectors onto these left and right eigenspaces. So if I multiply with this projector here from the left, I get a projection onto these left eigenspaces. If I multiply from the right, I get a projection onto the corresponding right eigenspace. Now, it's important to pay attention here a bit that it does not preserve this grading. So this decomposition here into the subvector spaces, which is due to the fact that here I multiply with a 1, and here I multiply with a Y, which is an element of CL1. So here I change the K in one component, while in the other one I don't. So these spaces here I cannot decompose into eigenspaces, but it turns out that the spaces which I can decompose into left and right eigenspaces have this particular structure here. So I can take this element here of the lower Clifford algebra, which is now homogeneous, has a fixed number of factors in this basis, and I can optionally combine this also with an element Y. So I have the sum of these two spaces here. Now there is a nice rule if I am in one of these spaces. So I pick this K here. Then I take an element V of this space. Then it follows that I have this nice commutation relation here with the Y. And this means that the left and right eigenspaces here actually agree if I fix my K. The only thing I have to pay attention to is that if my K is even, then the left eigenspace with eigenvalue plus 1 corresponds to the right eigenspace with eigenvalue plus 1. and minus corresponds to minus. But if my k is equal to -1, then I have to flip the sign. So the left eigenspace with plus eigenvalue corresponds to the right eigenspace with minus eigenvalue. Now, in particular, I'm interested in the case k equal 2 because I can identify this second subspace here with the spin algebra, or actually it's the same as the SO, the orthogonal algebra, and of course the same with dimension reduced by 1. And again, I find some nice splitting here of, well, first of all, these vector spaces. So this is a Lie algebra, of course, with the commutator defined from the commutator of the Clifford algebra. And later on, I will call this here G. I will call this smaller algebra here H. This is actually a Lie subalgebra of this one here. And there is this extra part here, which is actually not a Lie subalgebra. It's just a vector space. It's just a subvector space. But if I look at the Lie bracket, I find that this is a graded algebra. So if I take the Lie bracket between two elements of the Z here, I get an element of H. And if I take a Lie element with mixed Lie algebra, Lie bracket with two different elements, one from H, one from Z, I get an element from Z. So this is actually a graded Lie algebra that I have here. I can characterize these subspaces again with the help of this element Y here. And this is exactly what I've shown on the previous slide, that the left and right eigenspaces, their sign differs, or the commutation relation here differs depending on the K, which is different between these two. Yeah, so here the K is equal to 2, and here the K is equal to 1 because I have here this V vector space. Yeah, I can also write out the projectors. They then take this form here. Okay, so that was the Clifford algebra part. Now let's give a few introductory remarks on Cartan geometry. So what is Cartan geometry? The idea here is we start with the so-called Klein geometry, or homogeneous space, which is a quotient of two Lie groups. So G and H are Lie groups here, where this H is a closed subgroup of G. Think of the Sitter and Lorentz groups, for example. Then I can define this coset space here. So the space of, in this case, right cosets. And this is a so-called homogeneous space, so it carries transitive action of this Lie group G here. Now the next ingredient that I need is a principal bundle. This should be a principal H bundle. So you think, for example, here of the Lorentz group H, then this would be something like an orthonormal frame bundle, for example. And the principal bundle always carries the right action of a structure group, which is this H here, which I will write like this. And the infinitesimal action here is generated by the so-called fundamental vector fields, where these vector fields I denote like this, where this is an element of the Lie algebra. Now, the Cartan geometry is defined by so-called Cartan connection, which is one form on this field, on this principal bundle, which takes values in this Lie algebra of G. So this is different from a principal connection. For a principal connection, I would have values in the Lie algebra H, but here I have values in the Lie algebra G. And I need some requirements. The first requirement here is that at each element of this principal bundle, this map from PP to G that's induced by this one form here is a linear isomorphism. So you see here there is a requirement that the dimension of the Lie algebra, and therefore the Lie group G, is identical to the dimension of this total space of the bundle P here. Further, I need this equivariance condition. This is the same as in the usual gauge connection or Ehresmann connection picture this equivariance, but now with the group H only, which is a subgroup, since this is the structure group of P. And finally, also this condition here, that if I take one of these fundamental vector fields that generate the translation or the group action of this on the fibers here, then I get the same Lie algebra element back. So these are the three conditions that define a Cartan geometry. So yeah, as I mentioned, the dimensions of these different bundles are related. So the dimension of the fibers here is the dimension of H, because this is a principal H bundle. The dimension of the total spaces must be G, and the dimension of M must be the dimension of this coset space here. Now, how can you imagine this in a bit more pictorial way? So this is a nice picture that was introduced to me by Derek Weiss, who describes Cartan geometry via the hamster ball picture. So imagine, for example, we would like to describe the geometry of a two surface. Let's say this is a two-dimensional Riemannian manifold. And we would like to understand this geometry from the perspective of a hamster that's sitting in this kind of ball here. The hamster has the possibility to move within this ball, make a step forward or backward, make a step sidewards, and also just turn itself without stepping in any particular direction. And the hamster then just observes how the ball moves, or what is the path traced on this surface here. So in this particular toy model, we have a two-dimensional Riemannian manifold. The bundle here would be the orthonormal frame bundle, which is due to the fact that we have a Riemannian metric here. We can pick this bundle here. This is now a principal SO2 bundle in this particular case. And the position and orientation of the hamster, they mark a frame here. So you might think of the forward direction here. That gives a unique vector, which we can, of course, normalize with a metric. And then think, for example, of the vector pointing towards the left that completes the frame. And of course, if the hamster would turn here, that would be just turning the frame while staying at the same point. Now, what are the degrees of freedom that the hamster has? So, well, first of all, of course, as I mentioned, it can just turn around. That's basically then just moving within the fiber while keeping this point P fixed here. And the other kind of motion is what we call rolling without slipping. So this means like making a step in some arbitrary direction, and then having the ball like ideal friction rolling along this surface here. Now, if we look at these infinitesimal motions, basically, then what are these? So the complete set of motions that the hamster can perform correspond to this algebra G here. This is this larger algebra, the SO3. So this includes also the turning around its own axis. And this is, of course, are the three-dimensional motions that the sphere here can perform. So the sphere can rotate in space. Then we have the rotations which fix the point P, which do not move this. Sorry, not the point P, but the point X on the base manifold. The contact point is the subalgebra SO2, where the hamster just rotates, and the quotient space here of these algebras is then given by the Z, which is just a tangent space to this sphere here. And of course, the sphere itself is just a quotient space. This is the coset space here. And so we can fully describe the geometry M actually by this motion of the hamster ball. So this is the pictorial way how Cartan geometry describes the geometry of space. But of course, here I would like to apply it to space-time. Now for space-time, again, I have a Lorentzian in this case, Lorentzian manifold now with a metric here, and also, of course, the orthonormal frame bundle, which looks like this. And in a similar way, I can split the tangent space at each point of this orthonormal frame bundle into some vertical space where I have the infinitesimal Lorentz transformations that do not change the point. And I have some other space which define my translations, which is basically what happens when the hamster makes a step. And this space is actually canonical. This one is not canonical, but this space here is obtained if we have the if you compare this with the splitting of the, for example, well, I call this here Poincare algebra, but actually I should have spoken here of the Sitter or anti-de Sitter algebra, because these are the ones I will be working with, not actually the Poincare algebra here. So where this is Lorentz algebra, and these are essentially something like the translations. And this relation here is established by this Cartan connection. This is here the usual Lorentz connection, and this one here you can interpret as the, well, in this case, it's the solder form on this bundle here, but if you project this down, it would be something like a tetrad. Now then there are the fundamental vector fields, which basically act as the inverse of this, because we have at every point, we have an isomorphism here between this G and the space, so we can simply invert this relation here in every point as well. Yeah, and the geometry is now again encoded in this Cartan connection. So these were the mathematical preliminaries, and let me now come to how I will apply this to these different actions that I mentioned in the beginning. Let's first have a look at the Stelle-West action and how one can define this in a proper geometric way. So here I will take the spin PQ connection. So this is just a well, usual gauge connection or Iris-band connection on a principal G bundle in this case here, with of course then values in the Lie algebra G. For the Stelle-West action, this and this P and Q, of course, in this case, correspond to the de Sitter or anti-de Sitter algebra or group. Well, actually, it's a spin group in this case. For the Stelle-West action, we further need a field Y, which is I call it here a vector field. Actually, it's a zero form, so it's actually a scalar, but it takes values in this vector space V here, which is now this 5-dimensional vector space, and it's chosen such that this is normalized with respect to the 5-dimensional Minkowski metric, which can be either signature 4, 1 or 2, 3 now in this case, and I normalize it to be equal to +1 here, this norm. And finally, we need a Lagrange multiplier, which is now just a scalar on this P. Yeah, to be more precise, actually, I should also say that these are equivariant, of course. Now, from this A, we can define the curvature, well, usually the curvature of an Iris-band connection, as this, where by these brackets here, I mean that I take both the Lie algebra bracket and at the same time the exterior product of the forms here, of course. So this gives me a 2 form. And now this Y here defines the Lorentz subalgebra in here. So if I look here at the stabilizer of this Y, so those transformations that keep the Y unchanged, then this gives me a subalgebra which is the Lorentz algebra, or the Lorentz group actually, if I do it at the group level. And this defines in a particular bilinear form on this which I call kappa Y here, which is non-degenerate on H. So here you can think of a combination of the killing form with the Hodge star operator on the Lorentz algebra. These are essentially the ingredients that enter here. And then the Stelle-West action can be written like this, that we take this curvature here, put it into this form here, and we need here the Lagrange multiplier to enforce this condition here. So this is the well, basic structure of the Stelle-West action. Now for the MacDowell-Mansouri action, we go a slightly different path, and the most geometric interpretation for the MacDowell-Mansouri action is by looking at this as a Cartan connection. So here, instead of a principal G bundle, we have a principal H bundle, but still a G-valued connection, which we can now decompose into these two fields here, Lorentz connection and this solder form in this particular case. Now again, the curvature is defined exactly the same way, but via the decomposition here, since we have explicitly split our Lorentz algebra in this form here, H and Z, we also have a decomposition of the curvature into these spaces. And this one here, what you find here, this is just the curvature of the Lorentz connection plus this commutator of these E's, which is again H-valued. And here for the Z part, you simply find the torsion of this connection omega. Yeah, and then the MacDowell-Mansouri action only takes now the H-valued part. So here we have explicitly need to do the symmetry breaking. We disregard this part here, and this star here is the Hodge star on the Lorentz algebra here, and the trace is just a killing form basically. Now for the Palatini action, we usually don't regard these fields as a Cartan connection. We just treat them independently. We have a spin connection and a tetrad field, and of course we look at the curvature of the spin connection here, and we can of course also define the torsion. And now the Palatini action, I have written a bit more suggestively in this form here. So let me explain this a bit. So this is the usual Palatini term, basically written in this form here. I have omitted here, there's of course a free factor as well, which corresponds to the gravitational constant. I have omitted here all numerical factors, I have to say, and I'm looking only at the vacuum part of the action because I'm only focusing on the structure of the geometry behind and not so much on the coefficients and the matter coupling, of course. So this is the usual Palatini term here, and here we have a second term, which is a term for the cosmological constant. Again, here I have omitted any constants, an actual constant here, because I've basically absorbed this constant into the definition of this of the Lie algebra, where we can basically put an extra factor here into this commutator if we wish. If we expand this Lie bracket, then this is where we would where this numerical factor would enter here. Finally, for the Plebanski action, we have again a bit different structure. We have this spin connection, again this Lorentz connection, but now we have a two-form field here, which takes values in this Lorentz algebra. And we need an extra condition in order to be able to identify this two-form here as the E wedge E that was in the previous action. So this extra condition here we can get if we take a Lagrange multiplier on this sigma here, which is, well, let me not write it down because it's a bit technical. So it's basically something like a symmetric trace-free bilinear form on this on the Lorentz algebra that we need to add here. We have the Hodge operator that satisfies this relation that it squares to -1. And this means that its eigenvalues are plus and minus I. So that means that we cannot split H itself into these eigenspaces. We actually need to complexify if we want to split into this into such eigenspaces. So in the following, we will regard this sigma here as a complexified field. And if we do that, we can split both the curvature into what is then called the self-dual and anti-self-dual parts, and the same with the sigma here. which basically means that the eigenvalues with respect to the Hodge star plus I and minus I here. Yeah, and then finally we end up with a Plebanski action where we actually need only the self-dual part. It turns out that these two are linearly independent from each other if one writes this action out, so we can just take one part. Here we have the Lagrange multiplier that ensures that we can recover the tetrad for any solution of the field equations we get from here. And we have the part which is reminiscent of the Palatini action, here the curvature part, and here the cosmological constant part. So how are these related to each other? In fact, one can nicely get from one action to the next if one performs the symmetry breaking. So if I explicitly fix this Y field here, choosing a gauge essentially, where this is equal to one direction, which I call here E4, then I get the MacDowell-Mansouri action. If I omit some boundary terms, so if I expand this MacDowell-Mansouri action in the H and Z decomposition, I find that compared to the Palatini action, it has one more term, which is this R wedge star R. But this is the Gauss-Bonnet term, and this in 4 dimension, this is topological, so I can omit this from the action. And finally, I do this. I call it separation, where this is decomposition into these eigenspaces. Well, I use the word separation here because it's basically the title of the paper by Plebanski, where he introduces the split here. Now, how can we combine this? How can we write this in a unified way? Now, and that's the actually interesting work that we have been doing here. So let's now look at the Stelle-West action again, and let's take a look at the dynamic of fields. So basically this connection here, the symmetry breaking vector field and the Lagrange multiplier. So as I mentioned, the Lie algebra, which I called G, I can identify with this second space here, second subspace of this Clifford algebra, on which I have, of course, also the group G acting. I can embed this into the full Clifford algebra. I can later enforce this condition that it's in the CL2 part only by Lagrange multipliers if I wish to do that. The same with the symmetry breaking vector field. This Y I can also interpret as an element of now the first part of the Clifford algebra, because it's just an element of the vector space V, or it takes values in this vector space V. So again, it's a Clifford algebra valued field on this P here. And I still have the Lagrange multiplier, of course. Now the curvature here still can be written in the same way, where here this is now the commutator of the Clifford product. So this is how the Clifford algebra is related to the spin algebra. Actually, I could, in fact, even omit this factor 1/2 and replace this commutator here by the Clifford product in this particular case, because the Clifford product of or the anti-symmetry is already guaranteed here by this wedge product. So it's in any way already anti-symmetrized. So I could just omit the brackets and the 1/2 here. Now I can take this product here. So now all of these elements here are Clifford valued. Y is Clifford valued, F, and of course, the second factor F as well. So here what I get is a 4 form, which now really takes values in the Clifford algebra. And here I'm writing just very generically the full Clifford algebra, because it has components that lie in different subspaces. So here I've been confined to CL2 and CL1, but if I multiply out all of these, then I actually get components that lie in different subspaces here. So this is a bit of a messy object here. So what can I do with this object? Well, I can now take this object and multiply it with another Clifford element, namely this omega here, which is this volume element, and then I can take the trace over this. what happens if I do this? So first of all, this omega times y is basically just this volume element of the smaller Clifford algebra. And here I take the trace, and as you remember, the trace is non-vanishing only on the 0 subspace. So only the part of this whole expression here, which is proportional to the unit element 1, will contribute here. So here for this second term, this is kind of clear. So the 1 will of course contribute, and the y squared of course also gives us something proportional to the 1, and this is just the enforcing the constraint that this y is normalized. If you look at this here, then the question is, when do we get here a 1 element? Well, this object here, this volume form here on the smaller Clifford algebra, you can think of this as the product of 4 of the basis elements, where the basis elements now are exactly the basis of the orthonormal space to this y here. So this is just the 4-dimensional subspace which is equipped with a Lorentz metric. So yeah, something like E0, 1, 2, 3 you can imagine here. So in order to get 1 element, I have to kill each of these factors, which basically means that here the only thing that contributes is the antisymmetric combination of a product where in this F here I have components 0, 1, 2, and 3. So this is essentially contracting with a Levi-Civita symbol with 4 indices basically, and this is exactly what we get also if we have the usual form of the Stelle-West action. There's basically just an epsilon in here, which is exactly what appears here as well, if you think of this in components. Or in other words, this is this form kappa that I introduced before. So this is a way how, in my opinion, it's quite elegant to write the Stelle-West action in this form, because it's basically just the product structure of the Clifford algebra that gives you automatically this product, or this bilinear form here with the trace. Yeah, and of course, as I said here before, in principle, we could allow these A and Y to have also values in other components of this Clifford algebra. This would be an extension, but we can also, if we want to reduce to the classical Stelle-West action, we can enforce this with Lagrange multipliers. Now, if you want to go to the MacDowell-Mansouri action, we can use the decomposition I introduced in this omega and E, and it turns out we can actually decompose this E and omega, this A into E and omega with these projectors, and we can do the same actually with the curvature. And if we do this, then we can keep in mind that this omega y, which was introduced before, so this y here is a fixed Clifford algebra element, but it's takes then this form here. It actually commutes with any element of this smaller algebra H, and the commutator, or sorry, not the commutator, but this product here is actually the same as applying the Hodge star within this Lorentz algebra here. So if you compare this briefly with this action here, then what you see here, you can already identify this will be something like Hodge star acting on F, and then the trace over that, which is the killing form. This is where we want to get, of course, because then we can write it in the following form here. If we fully expand everything, we get to this very nice form here, where this is essentially indeed representing the Hodge star. This is the H component. So basically, if we start from the MacDowell-Mansouri action, the Stelle-West action, or we multiply this out here, then if we multiply and we find that the y here cancels everywhere under the trace, and the only term that remains is actually the Stelle-West action I have shown you before. So this is a way of having the MacDowell-Mansouri action. Well, not quite yet. It's call this proto-MacDowell-Mansouri action here because it still depends on the y. It is actually the Stelle-West action in disguise here. But if we do a gauge fixing and we fix this element to be E4, we basically just fix the Lorentz algebra within the larger algebra, then we just get the classical MacDowell-Mansouri action, and you see this is just the FH that appears here. So this is just one way of writing this action. Now, if we want to go to the Palatini action, well, let's take this one step further. Let's do the splitting for this for the omega already, and we can write out then the curvature now explicitly using these projectors here, where I've now again used this y here for the symmetry breaking. Now, if you see here, in particular this term here, you would see that there is a difference now from the classical MacDowell-Mansouri case going to the Palatini case, which is in the fact that this y here is now actually a field and not a constant. So it's not just E4, but here I've actually have a field in here. So the question is, what happens if I act with a d, with an exterior derivative on this? So of course I get dy terms here. Now these dy terms, they turn out to be elements or take values in this orthogonal field due to the fact that this y squared is fixed to 1. So this is imposed by the Lagrange multiplier. So the dy, once I impose the field equations, will be an element of this orthogonal space here. And this means that if I multiply everything out in the end, it will cancel under the trace, which is a nice property. This is due to the fact that, well, again, I use the y and the projector under the trace, and so these terms will cancel. And well, I use now the same expressions here. I don't write out the action again because it's basically just taking this r here now with the wedge of the e and so on. So this gives me a Palatini-like action. Let me call it again a proto-Palatini action because there is still a gauge vector in there. But if I fix this to E4, then of course I get just the Palatini action here, which is not very surprising because I've started from something like the MacDowell-Mansouri action. Now finally, for the Plebanski action, now this is where things get a bit more difficult, and also more interesting, I would say. So the dynamical fields now are the spin connection and the area element, which I again now interpret as taking values in some Clifford algebra, where these are now Lorentz algebra valued. So I am here in the smaller Clifford algebra, but in fact I can embed this into the larger one. Oh, there was a mistake. This should of course be 2 forms here, not 1 forms. Now again here I can enforce this this condition that this is an element of the Lorentz algebra with Lagrange multipliers, or I can use projectors as I did before. Yeah, and I can also write out the Lagrange multiplier term that I need. This is, yeah, can get a bit lengthy. I haven't written this out here. This is something we need to write down explicitly, but this can be expressed as well. Now the actual interesting part happens when you look at the split, where we want to do this split into the self-dual and anti-self-dual parts. So the Hodge operator, as I mentioned, can be expressed as a multiplication with this element omega y here. So this gives us the after complexifying usually these eigenspaces. But now in this Clifford algebra approach, what we can do here is we can write this out as a product of the volume form in the larger Clifford algebra with this y here, and we can write it, if you expand it like this, we can pull out the omega under the trace, basically, write the omega in front, and then instead of the omega, or the omega y, we have the y acting on the different components. So this becomes now our projector. And if we do this, so look at this projector, it turns out that this projector, because y squares to 1, it has eigenvalues plus and minus 1. instead of plus and minus I. And the spaces that we can decompose is now not the complexification of H, but it's a subspace of the Clifford algebra, which takes this form here. It has the Lorentz algebra and the Lorentz algebra multiplied with this Vy here. So this is a different subspace that we decompose here. We have a different decomposition, which we can then with the map with omega here map to the conventional one. So this gives again a split of into eigenspaces, which I've now written like this. For now, this R plus and R minus take values in the corresponding eigenspaces of this vector space here. Yeah, now again I can write down this let's call it Plebanski action, which of course I've just omitted again here for because it's again lengthy if I write down explicitly all the projectors. But it depends on this gauge vector y here. And if I fix that, well, then I guess I get the usual Plebanski action back here. Slightly different formulation, I have to say, because I have slightly different space here. But of course, the structure is still the same and the equations are equivalent. Now, if I look now at these actions here, I have again the 4 actions I showed in the introduction, but I have these 2 which are called like proto versions. Well, the proto MacDowell-Mansouri is just the Stelle-West in disguise, so there is this I have not written as a new theory, but basically what we have here are these versions of the Palatini and Plebanski action where we still have explicitly this field y in here, and they're all related to each other basically by doing here a gauge fixing. If you go from the left to the right, then we fix this y to the particular E4 vector, and here the steps down are exactly the same as previously. Okay, this brings me to the conclusion. So here I have expressed now different gravity actions through Clifford algebra valued forms, in particular the Stelle-West, MacDowell-Mansouri, Palatini, Plebanski actions. One can establish equivalence of these formulations here with the original form of the action, either by introducing extra Lagrange multipliers or using these projectors here. The actions have where we have the gauge vector field y in them, they have this larger symmetry group here, and we can break the symmetry by picking a particular gauge for this y that is induced by this Lagrange multiplier that tells us that the modulus of y must be equal to 1. And now the separation, the Plebanski action is done on a different vector space than on the usual complexification. Some outlook. So here the field y, well, here it's just fixed to be something static by a Lagrange multiplier. But in principle, we could also give some dynamics to this field y, and this might give some new phenomenology. Also, a bit more motivated by phenomenology is that we can, since we now have Clifford algebra elements, Clifford valued curvature, and so on, we can couple matter possibly a bit differently. So this we still have to study. This is just an idea for now. We can couple fermions a bit differently. Perhaps even replace this y here with a spinor field for the symmetry breaking. There's another project that we are thinking about. And in particular, if this happens to be a fermion that couples only to gravity, we could maybe understand this even as a dark matter candidate. So yeah, this is some work that's still a bit in progress. We will hopefully have a publication on this quite soon with Powell, and there you can then hopefully soon find more detailed calculations as well. So these lengthy parts that I have omitted here, you will then be able to find there. Okay, with this I would like to conclude, and thank you for your attention.
Thank you very much for the nice talk. Are there any questions?
maybe for those who are not so familiar with this big blue button, you can there is either a public chat where you can type, or you can raise your hand, as Paul has just done by clicking on your nick on the left, on your name on the left. Then you yeah, Paul, I see, has a raised hand, for example.
That's a raised hand or a clapping? I'm not sure.
Or is it the clapping hand? Oh, I think that's a clapping hand indeed. Oh yeah, I see. It's a different. Yeah, it's a bit hard to distinguish these.
Hello, Manuel. Can you hear me?
Yes, I can hear you.
Yeah, this is Joel. So let me ask a question. So I'm not an expert in this field, but just maybe a general question. Since at the beginning you mentioned the future outlook about quantizing gravity in general. So in your opinion, since you have 4 different actions, so basically, if I understand correctly, you somehow show that they can be related or can be shown equivalence through some manipulation. So, but practically, if you want to go beyond, if you want to like consider quantizing gravity, which one would be more politically accessible in your opinion?
Okay, that's a very good question indeed. So I have looked so far only at the classical picture here. So these by equivalence here, one should state that this is a classical equivalence at the level of the field equations.
Right.
So to quantize, I think yeah, the either, not sure, either the MacDowell-Mansouri or the Plebanski are rather good approaches, because so the basic idea I would have is something like a loop quantum gravity or canonical quantum gravity approach here. So which is also a connection-based approach. There one introduces a 3+1 split usually, and then introduces the so-called Ashtekar variables, which are also again a connection. And something like a well, not tetrad but triad field dual, basically the canonical variables that I introduced there. And I think yeah, either the MacDowell-Mansouri or the Plebanski are the easiest related to this approach.
I see. So it's really I mean about whether the action is more based on the connection basis, right?
Yes, exactly.
Okay, thank you.
Any other questions? Oh, there's one in the chat. Thanks for the informative talk. Would you mind recap the Cartan geometry in the hamster case? I wonder how you got a 3-dimensional space for the position of the hamster, if I got it correctly.
Okay. So it's not actually the position of the hamster that is the 3-dimensional space, but basically the 3-dimensional space are the degrees of freedom that the hamster motion allows. So it's let me actually go back to the hamster slide to then we can see this maybe a bit more clearly. Okay, so the ideas here is the following. The sphere here, I mean, this is just a 2-sphere, has a symmetry group which is SO3. So the SO3 describes the possible rotations of the sphere, and this 3-dimensional space is actually this space of rotations of the sphere. So and how are these rotations infinitesimally described? So if I consider the correspondingly algebra, which is the SO3, then this is just a tangent space to this Lie group SO3 at the 0 point. And these motions that the sphere can perform are basically the degrees of freedom of the hamster. So if the hamster makes a step forward, I will basically make a rotation of the sphere around this axis that is above the hamster, that's like perpendicular to the hamster. This is one direction. then if I take an axis that is that goes through here, then this is if a hamster makes a step sidewards, then I would basically rotate the sphere around this axis. And if the hamster just stays where it is, does not make a step in any direction, but just rotates within the sphere, that's the third axis here. So basically, this three-dimensional space is not just not the position space of the hamster, but it's basically the space that consists of both position and orientation in the sphere. Yes, exactly. It's a rigid body group. Yes, correct.
Other questions? It seems not. Then let me start the recording. Thank you very much again.